Our next topic is roots, or we could also say radicals. And what we would be talking about is extending the idea that we've seen in the past about square roots. So a little reminder here at the beginning that we've got a number, b. We call that a square root of the number a. If b squared is equal to a. So notice that there's a sort of turnaround in that phrasing. B is a square root of a. If b squared gives us the number a. So we can actually rephrase square roots as a question. Just to comment though on what this means, we've got, just as a numerical example, 5 squared gives us the number 25, but we also have the number -5 that if we square that, we also get the 25. So we have two different answers that could come about from a square root depending on how we might view things. This is a bit of an issue here. So we could have a positive square root where we say, well, the square root of 25 we could view as 5, but we could also say that the square root of 25 would be a negative number, like -5, and we don't want to do that. So we'd rather have that negative very clearly associated out in front of our square root, so that what we're really going to do when we talk about square roots, and you might recall this, is we're going to talk about a positive answer. Whatever it is that we've got coming out of our square root has to be a positive answer. So we can give our rule very formally as saying something like the square root of an a squared has to be a positive answer. So we're going to force that to happen no matter what. We're going to force that to happen using absolute value bars. And the square root and that power of 2 are unlocking each other. Or another way of saying it is we're going to be looking for what positive thing can we square in order to get a squared. That's a really nice question, kind of answers itself if we actually listen to what we say. What positive thing squared gives us a squared? Well, we know that a is going to be at least part of the answer, but because it has to be positive, we force that to happen by putting those absolute value bars. So to look at some examples where we have this nice kind of interaction. The square root and the power of 2 are undoing the effects of one another. They're unlocking each other. And so the only thing we have to worry about is whether our answer is positive. In this first example, that square root and that power of 2 unlock each other. What do we square in order to get 0.2 squared? Well, very directly, we get 0.2. What do we square in order to get -0.2 parentheses squared? Well, just as that question is asked, we get a -0.2. What do we square in order to get a -0.2 parentheses squared? That's what we squared. But our answers have to be positive. Our answers have to be positive. So this is not an acceptable answer, not yet. Officially speaking, we need to put those absolute value bars in there. And once we put those absolute value bars in there, we actually can simplify this particular answer so that it ends up being 0.2. That is going to be the positive thing that would be squared in order to give us this business. What do we square in order to get x squared? Again, the question answers itself at first. We square x in order to get an x squared. Well, now here's where we've got another element of the rule being very important. Do we have a guarantee that x is always going to be positive? Would anybody be able to pick an x that is something other than positive? Sure, There are infinitely many negative choices that could be made for x. So this answer is not guaranteed to be a positive answer. But that's what we need. So if that answer alone is not good enough, then the absolute value bars will force this x into being a positive thing. And sadly, for the moment, that's the best that we can do. Now, eventually, we're going to be let off the hook with something like this, but really want to emphasize that that is the official formal version of square roots, that we're going to be giving positive answers for those. And for right now, I'm kind of dogging things in these examples in that respect. Eventually, I'm going to let you off the hook as far as this is concerned, and we're going to make things a little bit more direct to work out. But for the time being, what do we square in order to get x minus 1 parentheses squared? Well, officially we get an x minus 1. But there is, again, no guarantee that that will always be a positive answer. So I must force my answer to be positive by having it put inside of absolute value bars. Again, I am nitpicking things at the moment because of that official rule that we have, and let's leave that official rule up here at the top for just a moment. One of the things that they might try to do to you to see if you're paying attention and know that rule properly is ask you something like this next example, the square root of negative 1. Well, again, the basic question, what positive thing would we square to get a negative 1? Well, if we square a positive, positive times a positive is a positive. If we square a negative, negative times negative is a positive. 0 times 0 is 0. So as far as real numbers, we don't have any real numbers that would be answers to that square root. For the time being, we can't actually answer that particular question. We would have to have a much larger perspective on math and on numbers in order to have something that could act as an answer to the square root of negative 1. Working with just the real numbers, that square root of negative 1 does not have an answer. So we want to watch out for where our negative might be as it appears in the problem. Does it appear underneath the square root, but inside a set of parentheses? Does it appear underneath the square root, but not inside a set of parentheses? And like we'll see down here in just a moment, does it appear out in front of the square root? We want to pay attention to those things. But again, the basic idea there at the top, we've got our rule, and essentially we're asking ourselves a question that is, what positive thing do we square in order to get a such and such? What positive thing would we square in order to get a 400? Well, with the assistance of our calculator, or quite possibly because you automatically know that, we're looking at an answer of 20. In the next example here, looking just at the square root of 441, we're going to ask ourselves, what do we square? What positive thing do we square? What positive thing do we square in order to get the 441? Well, again, if you know it, great. With the help of a calculator, we find that that square root by itself is the number 21. But that square root does happen to have a negative out in front. So the negative that is out here at the front doesn't affect us answering the question that we've been asking in all of these other examples. But it doesn't go away, so that negative is still going to have to sit in front of the answer that we came up with. So the complete answer, negative square root of 441, negative 21. Again, we want to make sure we're careful about our negatives, as always. But this idea, the question that we have up here at the top of the screen, that is something that we can extend. We do not have to just limit ourselves to mentioning a squared as our power, a power of 2. We can have any sort of power that we might want, which means that we can extend the idea from a square root to all different sorts of roots. So we would have to name them based on the important power that would be going on. So generically speaking, nth root, that's referring to the important power that is going to be built into our question. Power n. So the nth root, for instance, the fourth root is going to look like this. We're going to make mention of that special power out on the little front stoop of our square root symbol. It's not going to be a square root symbol anymore. We'll call it a root symbol, or we'll call it a radical. So the fourth root of 16. We're looking for a number raised to the power of 4 that will create the 16. So what number would that be? Well, it turns out that's going to be the number 2. 2 to the power of 4 gives us a 16. So we can come up with extended rules to handle any type of root, or we could also say any type of radical. But one rule will not do. Like we saw with square roots, that had an extra little something in the question that we asked, leading us to a positive answer. And as it turns out, anytime that we're referring to an even power, so square root, fourth root, sixth root, 28th root, anytime we're referring to an even root, our answer is going to have to be positive. So we might still need those absolute value bars when we're being nitpicked like that. Any of the odd roots, we don't have to worry about the issue of our answer being only a positive. Our answer is allowed to be anything, whether positive or negative. We just have the unlocking that takes place. And once that unlocking takes place, we would be done with those odd roots. It is only these even roots where after the unlocking, we may need to use our absolute value bars to force our answer to become a positive answer. So these two rules here take care of any kind of root, including a square root, and now open us up to having many more different examples that we can look at, like these. Starting out with the top example here, we have a 3 sitting out on the front porch, which means that this would be referred to as the third root, or we could also say the cube root, because that power of 3 had a special nickname with cube. So the third root, or the cube root, of -4, parentheses, cubed, or to the third power. Because that number out on the front porch matches the number that is the power that's underneath, there is this unlocking that takes place. And according to our rule at the very top of the screen, because this is an odd root, we can just unlock things and call it a day. Because this is an odd root. Because the number out on that front porch is an odd number. When the unlocking takes place, if we get a negative, all right, no big deal. That is, in fact, a necessary part of our answer. A 5 sits out on the front porch here of our radical symbol, meaning that this is a 5th root. The number out there on that front porch matches the power that is underneath, which means that this unlocks directly. And when we unlock those, you could think of it as mentally erase the radical symbol and erase the power. And what you would have, if you do that little bit of mental erasing, would be parentheses 2/3, We don't need the parentheses as part of our answer. We can just write that fraction 2/3. This does not automatically have a power underneath that matches the power that appears on the front porch of our radical symbol. So in this particular case, we would either have to come up with an answer with or without a calculator. With a calculator, if we could type something like this in, we'd be in great shape. Sadly, we do not have that possibility quite yet, unless you know a little trick that I haven't mentioned yet. Which means that what we'd have to do is essentially try to build some possible answers to see which might work. And we know that 1 is not going to cut the mustard. 1 to the power of 4 is going to give us 1. So we try 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. We also happened to see that a few minutes ago in an earlier example. 2 doesn't work. 3 times 3 is 9, times 3 is 27, times 3 one last time gives us 81. Doesn't quite get us there. 4 times 4 is 16, times 4 again is 64, times 4 again is 256. So what we have going on here, and just to try to emphasize how we've come up with this, seeing as how there are a lot of 4s that are appearing, we have built ourselves the answer to this by considering the basic idea behind this root, the 4th root. We needed something that was going to be raised to a power of 4 and generated the 256. So we found that the number that we needed was a 4. That is a positive number, so we are good as far as our earlier comment. Even roots have to have positive answers. So this is in fine shape as far as that answer goes. And then, moving on, another problem where we have an odd root and the number out in front matches the power underneath, so this would automatically unlock. After that, we have a problem where we do not have a number out front, which goes back to the first part of our conversation. That means that we are looking at a square root. If we do not have a number out front, square root. So square root of x squared, square root, and a power of 2 unlock each other, give us an x. But again, we've got that comment from before, as well as the extended version of that comment at the top of the screen that says our answer needs to be a positive answer because this is an even root. So this time we would need those absolute value bars. The cubed root of x cubed. This is an odd root. There is no special qualification going on here. The number out front matches the power underneath, so this unlocks automatically and gives us x. Because there is no special qualification on the rule for odd roots, that is a perfectly acceptable answer. I do not have to do anything else to it. 4th root. Like we've said before, those even roots have to be positive answers. So when the unlocking takes place here, we get an x minus 1. There is no guarantee that that is a positive answer, so I must put in those absolute value bars, officially speaking. Still haven't let you off the hook as far as that goes. And this could be the last one where we've got to worry about that. In this last example here, we've got a 5th root yet again, so an odd root. The number out front matches the power underneath, so the unlocking takes place and gives us y. Odd roots do not have any sort of special issues going on, so the unlocking takes place, we're done, move on. From here on out, the examples that we're going to do, we're going to try to keep things a little bit friendlier. We're going to automatically assume that any of our variables are already positive, and that means that we no longer have to worry about including these absolute value bars in any of those answers. That just kind of makes the rest of the conversation move along a little bit more smoothly. But it is possible that in the future you would have to worry about those sorts of things. Again, going back to that top rule where we have even roots. They must have positive answers. Even roots must have positive answers. Even roots must have positive answers. This might be something in the future that you do have to worry about remembering. But for the rest of our examples here, we're going to let ourselves off the hook. What we've got going on is unfortunately more involved than those rules and the examples that we've seen so far might suggest. We don't always have the unlocking that takes place and gives us a very nice answer. But that does give us at least a nice thing to try to work with in terms of simplifying our radicals as much as possible. And for right now, we're also going to restrict our discussion to just the square roots. Make things, again, a little bit friendlier to us and get ourselves in the groove of working with roots in general. So we've got 3 additional things to worry about when our square roots don't automatically match up with a squared power underneath. If there are any factors that have nice square roots, I would want to break them off. I would want to simplify those nice square roots. And any of the not nice square roots, like the square root of 2, those would be left alone. So the square root of 16, that has a nice answer of 4. The square root of 2 does not have a nice answer, so it would be left alone. And then, like we've seen in the past, we have special issues sometimes with fractions, and that goes with the rule number 2, rule number 3 that are mentioned here. Fractions. As far as fractions and square roots, we are not allowed to have fractions underneath square roots as a final answer, or at least for right now, we're going to say that. As we become more familiar with algebra, we can be a little bit more relaxed about that sort of thing. And we can also be a little bit more relaxed in the future, but not right now, only in the future, about this third rule, where if we have any sort of roots or radicals, again, interchangeable, we don't want those radicals, those roots, to be in the denominator. So any sort of roots that show up, we're going to need a way of working with them if they're in the denominator. We're going to need a way of being able to get rid of them. What this leads to, other than our nice unlocking rules for odd and even roots, are 2 other rules to help us out. We have a rule that allows us to break apart and recombine things based on multiplying. And we have a rule that allows us to break apart and recombine things based on division. So this gives us a little bit of flexibility to try to break a problem into more bite-sized pieces by, for instance, breaking things apart using factoring, or breaking things apart based on doing the square root of the numerator and the square root of the denominator separately. We get those bite-sized pieces taken care of, and these rules also allow us to recombine any sort of remaining square roots back together so that we can have a clean-looking answer. So we want to keep these in mind as we begin to look at a few examples of some more sophisticated simplifying. So down here at the bottom of the screen, let's look at something that connects to that first new rule. Any nice square roots we want to take care of. Any square roots that are not so nice are going to be left underneath the square root. So in this first example, we only have the a with a power of 11. So we don't have a power that matches the square root. But we do have a bunch of square roots that we can break off and basically have expanded that a to the power of 11. So we break off an a squared because that'll have a nice square root. And we'll break off another a squared and another and another and another. And that'll leave us with one last a, no extra power going on there, so officially a power of 1. All of those a squareds, because they are underneath the square root, will have unlocking that take place. The very last a that's by itself underneath that square root, though, does not have any nice unlocking that takes place and would remain underneath that square root. And so that what we get as far as a nice direct answer is an a with a power of 5 and a square root of a. We have unlocked as many of the nice square roots that show up as possible. Now, this is a long way of having to work through problems unless we do what is a very good idea for any math person to do, and that's to look for patterns. What we can do is we can shorten this process up a little bit by recognizing that our power here of 5 is related to our power of 11 and the fact that we are working with a square root, which means that we've got an important power of 2 that is also in play. So with the 11 and the 2 that's important because this is a square root problem, and the 5 that we see in our answer, the way that things could be put together in a very short and simple way is that the original power of 11 divided by the 2 that comes about because this is a square root problem would give us a mixed number of 5.5. The 5 referring to the nice normal a with a nice normal power of 5, and the 1/2 part of this telling us that we're going to have a leftover square root with just the a underneath of it. So that short way, that shortcut, is something that will be nice for us to use if we see an example that has a little something like this in the future. But let's also look at another example of that same idea, but one that involves numbers. Here we have a 5 square root of 18. Well, one of the first things that we want to remember here is that the 5 being side by side with that square root does officially mean that's 5 times the square root of 18. The square root of 18, that does not have a nice answer by itself, but if we consider breaking the 18 apart, we would want to think about any numbers that could be factored from the 18 that have a nice square root. So we have numbers with nice square roots. 1, not helpful. 4 has a nice square root. 4 doesn't go into 18. 9 has a nice square root. 9 goes into 18. 9 goes into 18. So if we take the 18 and we break it apart as a 9 times 2, then we have our pink rule there in the middle of the screen that tells us we're allowed to separate the square root of 9 so that the other piece would be a square root of 2. Because the square root of 9 has a nice answer to it, we can work that part out. The square root of 9 is 3. And as we've seen in other kinds of problems, 5 times 3, it sure is a lot neater and shorter for us to go ahead and say 15. And we don't have to use the multiplication dot. We can go ahead and leave that off and simply have the square root of 2 showing up next to give us a very short answer that takes into account that first rule referred to still up there at the top of the screen just barely. anything under the square root that can be broken off and has a nice answer. Anything that we can break off that has a nice square root, we want to break it off. We want to do that nice square root so that the answer that we get is just a little bit nicer, a little bit neater, a little bit cleaner looking. And so in this particular case, looking at the 18 under the square root, if there is any nice number that can be broken off the 18 that would have a nice square root, we're on the lookout for that. And we do, we have a 9. Square root of 9 is a nice answer, so we break that off. Break off that square root of 9. Leaves us with that square root of 2 still showing up, but hey, better than having a bigger number underneath of our square root symbol. That first rule is one that is used very often, while the second and third rules still showing up there on the screen are not as widely used. So how about a little something that incorporates both of these earlier examples into one? Something with a little bit of number stuff, something with a little bit of letter stuff, where we would have to worry about simplifying as much of our square root business as possible. So we have our rule that says, first of all, we can break apart our problem as the square root of our number stuff, separated out from, and we're kind of jumping a step here. We don't literally need to separate these things out underneath a single square root. We can jump more to the heart of the matter and say, look, we want to look at these as 3 separate square root problems. And once we have those 3 separate answers, we can go ahead and recombine things together to get our final answer. So the square root of 32. We use a little color here to keep track of things. Let's say that we've got that square root of 32. We're looking for any number that we can break off of a 32 that has a nice square root. So a 4 would work, but maybe there's something bigger, so we just take a moment and consider anything that's bigger that might be useful to us. 9 would not be helpful. 16, well, we can break off a 16 from a 32, and that gives us a little bit faster path to our answer. Again, let's also be fast and just immediately break off the square root of 16 and separate it from the square root of 2. The square root of 16 has a nice answer. The square root of 2 does not. And so that takes care of part of what we need. The other parts that we've got going on here are going to be related to our number pieces. So for our A business, the shortcut that we had mentioned a few minutes ago said, let's take the original power. Let's divide by 2 because this is a square root problem. And this has a nice answer. It has a 5. And what that would mean for us is that we are going to have an A with a power of 5. So this completely unlocks. There is no leftover square root business that appears from that part. What about our B stuff? Well, our B stuff, shortcut says start with the original power of 19, divide that by 2 because this is a square root problem. When we do so, we are going to have a 9 and 1/2. So to have a little bit of a different appearance to that 1/2, let's use a different color. 9 and 1/2, meaning that we will have the letter B with a power of 9 because of that nice normal 9. But the 1/2 that is written in that awful pea soup color means that we will have a square root that also appears in this particular answer. Now, the only thing under our original square root problem had to do with the variable b. So the thing that's left inside of this square root is just going to be a single b. So we would need to take these portions and reassemble them into our answer. The way that they at first might look is not very friendly looking, because we would have square root stuff mixed together with variable stuff, and we'd also have square root stuff appearing in two different places. So this seems a little messy. We have our rule that says that we're allowed to combine square roots together, so why not take the square root of 2 and the square root of b and combine them back together so that that stuff is just a little bit neater looking, and we're going to put it at the end because it's much more convenient to put it there, so that the beginning part of our answer looks a little bit more normal looking to us based on our work with polynomials. 4, a to the power of 5, b to the power of 9. And at the very end, we get the new stuff that is left over from our current example. The square root stuff showing up at the very end, putting those back together into one square root means that underneath we would need both the 2 and the b. So the square root of 2b. Similar idea for the last couple of examples, but just kind of briefly highlighting the other rules that are mentioned here. We are not allowed to have a square root in the denominator, so we might say to ourselves from earlier, I know that the square root of 32 can be broken apart as the square root of 16 times the square root of 2, aka 4 square root of 2. And because I have seen that in the past, I recognize that now I can go ahead and slash out the square root of 2 on the top and the square root of 2 on the bottom in order to get a final answer. But we do have another way of looking at this particular problem, and that would be if we combine those square roots together. Well, this creates a separate issue that relates to the other rule for us to worry about. We're not allowed to have the square root of a fraction. So we're going to have to tinker with the fraction if we took this path. 32 divided by 2 is 16. So then, hey, that's nice. The square root of 16 gives us exactly that same answer of 4. And the last example also is kind of illustrating the same sort of basic idea, that what we have going on here originally is a fraction underneath that square root. And for the moment, what we'll do is we will take this problem and break it apart first into pieces and ignore the square root. So the number stuff, the x stuff, and the y stuff have all been separated out from one another, and if I simplify each of these, then I would get a 25, an x to the power of 15, and a y to the power of negative 18. This would be based on those rules that we had for working with exponents. So now that cleans things up for underneath the square root. What I would really have to have going on, though, is reintroducing that square root, and my rules let me do that by having 3 separate pieces to work with. The square root of 25, the square root of my x stuff, and the square root of my y stuff. The square root of 25 has a nice answer, kabam. The X stuff and the Y stuff are going to use our shortcuts. 15 divided by 2 is 7.5, meaning that we would need an X with a power of 7, and the 1/2, meaning we would have a square root of X left over. Our Y stuff also being handled with our shortcut. -18 divided by 2 gives us a -9. So our Y stuff would have to have a power of -9. And that gives us as our final answer a 5, X power of 7. Let's do our Y stuff next because that's more normal looking, and our square root stuff at the end. But because we've been dogged in the past before about having negative powers in our answer, we may need to worry about that same sort of issue, in which case we might write something along the lines of 5x to the power of 7 square root of x, since that is all normal stuff that would appear in the numerator, and our y stuff would be the only stuff that gets kicked downstairs to the denominator, and that power would turn into a positive power. So that would be another possible version of our answer, depending on what kind of instructions we might have had